developing next-generation research and technology, facilitating connections between AFRL industry and academia, unlocking innovation through a culture of collaboration. This is the AFRL Regional Network Midwest.
Hello, I'm Aditya Nechiyil, co-founder and CEO of Rescav LLC. Our team is tackling the challenging issue of detecting tampered integrated circuits, or ICs, which can compromise the safety and reliability of critical systems and infrastructure. Current available methods for the detection of tampered integrated circuits can often be slow, ineffective, expensive, or even destructive. Our goal is to address these limitations with the development of the Rescav system, a non-contact and non-destructive solution for the rapid screening and detection of counterfeit or tampered ICs. Our current experimental setup consists of two key hardware components, the resonant cavity and the vector network analyzer. In this project, we aim to evolve our current experimental setup into an enhanced prototype to incorporate additional components and an intuitive graphical user interface that will allow for the seamless integration and operation of the entire system.
Due to the globalization of the microelectronics industry and the lifetime extension of many weapons platforms in the Air Force, being able to assure the functionality of the electronics going into these weapons platforms is absolutely vital for national security. For instance, the B-52's first flight was in 1952, and it is expected to remain in service well into the 2050s. Part of assuring the microelectronics is testing to make sure that the Air Force is getting what they purchased and only what they purchased. Projects like these will help to ensure that no counterfeit parts or parts with malicious insertions can make their way into the DoD supply chain.
Over the first 6 months, we've made tremendous strides in developing and refining the Rescav system. Our primary focus was ensuring the system's consistency, accuracy, and repeatability, key factors for reliably detecting subtle variations in integrated circuits. We designed, fabricated, and integrated all the necessary components to build the Rescav system. This was followed by extensive testing to validate its performance and reliability. One of our first major tests assessed the thermal stabilization of the vector network analyzer, or VNA, which is crucial for stable, accurate measurements. We found that after a 3-hour warm-up period, the system reached equilibrium, allowing for reliable data collection. We also tested the repeatability of our automated lid mechanism, running 200 open-close cycles to confirm that no significant drift occurred over time. Additionally, we evaluated the system's resilience to slight variations in IC placement, verifying that it maintained accuracy despite small shifts. Once we confirmed the system's consistency, we performed blind validation tests with our AFRL collaborators. These tests demonstrated that the Rescav system, designed to match our earlier experimental setup, not only met the same level of performance, but also introduced automation that tripled the speed of measurement acquisition. Furthermore, the user-friendly GUI seamlessly integrates with the VNA and actuator to streamline both data capture and analysis. Beyond technical progress, we've also achieved significant milestones. Through the Ensign Foundry program, we engaged in 100 customer discovery interviews, uncovering critical defense and industry challenges in counterfeit IC detection, and refining our approach to address these needs effectively. Additionally, we earned second place in the program's pitch competition. Using the prize money from the competition, we purchased our own VNA, thus enabling us to conduct regular experiments in-house. Over the past 6 months, we expanded on our earlier work by building 3 identical Rescav systems, each composed of modular components like the cavity, lid, probes, and actuator. Variation in any of these components can lead to variation in the signatures captured by the system. For our application, it's crucial that every system produces consistent matching signatures. This is especially important for field deployment, where a signature captured at Site A must be comparable to the one captured at Site B. To evaluate this inner system consistency, we performed a series of component swapping experiments where we systematically swapped out one component at a time while observing the resulting impact on the captured signature. To quantify this variation, we calculated the standard deviation at each frequency point across the entire signature and multiplied it by 3 to get the 3 sigma range. As seen in our previous work, the intra-system lid open-close experiments showed very low variation, indicating strong repeatability within a single system. Similarly, the inter-day variation results revealed only a slight increase in variation over time, suggesting good temporal stability. Swapping probes did introduce more variation, but it remained within acceptable limits. However, when we swapped lids, the variation increased significantly, and the same trend was observed when swapping cavities, highlighting the need for tighter machining tolerances to ensure consistent performance across systems. The most significant variance was observed during inter-cavity testing with the actuator in place. This suggests that the current lid and actuator design may not be applying uniform pressure when closing, which can distort the signature. Future iterations will likely require a redesign to ensure more even and consistent pressure distribution across the lid cavity interface. These findings are helping us fine-tune the mechanical design and guide the tolerances needed to ensure repeatable, reliable measurements across systems. In the next 6 months, we plan to fabricate an updated version of the system with tighter tolerances and a redesigned lid closure mechanism, followed by a re-evaluation of the inner system consistency.